Welcome to this comprehensive guide for beginners on implementing basic data encryption and decryption in C# for securing game-safe files. We'll cover fundamental concepts and practical code examples. Understanding why encryption is crucial for game-safe files is the first step in protecting your game's integrity and ensuring a fair play environment. It safeguards against various forms of tampering and unauthorized changes. Encryption primarily prevents cheating and unauthorized modification of game-saved data, which is essential for maintaining a fair and consistent player experience. This protects the game's economy and progression systems from exploitation. While encryption adds a significant layer of security, it's important to note that determined individuals might still attempt to reverse engineer the game's code or encryption methods. This highlights the ongoing challenge in digital security. Let's begin by setting up our project in Visual Studio, which will serve as our primary development environment for writing and testing our C# encryption code. This integrated environment is crucial for our practical implementation. We'll create a new C# console application, which is ideal for demonstrating core cryptographic concepts without complex UI elements. This approach allows us to focus purely on the encryption and decryption logic. Crucially, we need to include the system, security, cryptography namespace in our C# project. This vital namespace provides all the necessary classes and methods required for performing our cryptographic operations, such as AES encryption and decryption. Now, let's dive into the fundamental cryptographic concepts that underpin our encryption process. Understanding these core principles is essential before we begin writing any code, ensuring a solid foundation for secure implementation. Symmetric key encryption uses the same single, secret key for both encrypting plaintext data into ciphertext and for decrypting that ciphertext back into its original form. This shared secret is central to the process. AES, or Advanced Encryption Standard, is a widely adopted symmetric algorithm known for its excellent balance of robust security and efficient performance. This makes it a popular and reliable choice for many encryption applications. AES supports key sizes of 128, 192, and 256 bits, offering varying levels of cryptographic strength. Larger key lengths generally provide greater security against brute force attacks, allowing you to choose based on your security needs. The secret key is paramount. It must be kept strictly confidential and secure at all times. Its compromise would immediately render your entire encryption scheme completely useless, exposing all your protected data to unauthorized access. An initialization vector, or 4, is a random value used with the secret key to ensure that identical plaintext encrypts to different ciphertext. This adds crucial entropy and prevents patterns from being recognized, significantly enhancing security. The 4 should be unique for each encryption operation to enhance security and prevent patterns from emerging in the ciphertext. Even if the same plaintext is encrypted multiple times, a unique 4 ensures different ciphertext outputs. Cipher modes dictate how the encryption algorithm is applied to blocks of data. They define the iterative process of encryption and decryption, influencing how plaintext is transformed into ciphertext and vice versa. Cipher blockchaining, or CBC, is generally preferred over electronic codebook, ECB. CBC avoids encrypting identical plaintext blocks into identical ciphertext blocks, significantly enhancing security by obscuring patterns and making cryptanalysis harder. Padding modes are necessary when the plaintext data isn't a perfect multiple of the cipher's block size. Without proper padding, the last block of data would be incomplete, leading to errors during encryption or decryption. PKCS7 padding is a commonly used method to ensure the data fits correctly into the encryption blocks. It adds extra bytes to the end of plaintext data, guaranteeing the data length precisely matches the fixed block size, preventing truncation. Now, let's look at the actual C# code for encrypting our data. We'll translate the cryptographic concepts we've discussed into practical, runnable code examples, demonstrating the implementation step by step. Key generation is critical. We use ES, create to instantiate an AES object, and then call generateKey to create a cryptographically secure random key. This ensures the uniqueness and strength of our encryption. It's vital that keys are never hard-coded directly into your application's source code. Hard-coding keys makes them easily discoverable and compromises the entire security of your system, making it vulnerable to attacks. Similarly, generate a random for using AS, create and generate IV, ensuring it's unique for each encryption operation. A unique for is crucial for maximizing security and preventing patterns in a ciphertext. For the encryption process, we first create an iCrypto transform object using ES that creates encryptor with our key and for. This object is responsible for performing the actual cryptographic transformation of the data. Next, a memory stream holds the encrypted data, acting as a temporary buffer in memory. This stream efficiently collects the ciphertext as it's generated, preparing it for subsequent storage or transmission. A crypto stream then links the memory stream with the encryptor, allowing us to write plaintext and receive ciphertext. This stream acts as a conduit, transforming the data as it flows from plaintext input to encrypted output. Finally, convert the encrypted data to a suitable format like base64 for storage, making it text-friendly. Base64 encoding represents binary data in an ASCII string format, which is ideal for text-based storage or transmission. Now, let's reverse the process and decrypt our data back to its original form. This involves taking the ciphertext and, using the correct key and for, transforming it back into readable plaintext. The first step in decryption is to retrieve the exact key and for that were used during the encryption process. These two components are absolutely essential for successfully reversing the encryption and accessing the original data. We then create an iCrypto transform object using ES that create decryptor with these retrieved key and for values. This decryptor object is specifically configured to reverse the encryption performed earlier using the matching credentials. A memory stream is initialized with the encrypted data ready for processing. This stream serves as the input for our decryption operation, holding the ciphertext that needs to be transformed back into plaintext. Similar to encryption, a crypto stream links the memory stream and a decryptor, allowing us to read the decrypted plaintext. As data flows through, it is transformed from ciphertext back into its original, readable form. Finally, convert the decrypted data back from its base64 representation to the original plaintext. This final step restores the data to its usable form, completing the full encryption and decryption cycle for our game-safe files. Effective key management is paramount for maintaining the security of your encrypted data. A strong encryption algorithm is only as secure as the key used to protect it, making key protection a top priority. Keys should never be hard-coded or stored in plain text within your application or configuration files. This practice creates a severe security vulnerability, making your encryption keys easily accessible to potential attackers. Instead, utilize environment variables or dedicated secure key management systems for storage. These methods provide a much higher level of protection by keeping keys external to your application's source code, reducing exposure risks. For Windows environments, the Data Protection API, or DPoP, offers a robust way to encrypt user credentials safely. DPoP is a built-in operating system feature designed for secure data protection, especially for local user data. DPoP leverages the user's key for encryption and decryption, tying the security to the logged-in user or specific machine. This ensures that only the authorized user or system can access the protected data, enhancing local security. Regular key rotation is another best practice that significantly enhances security over time. By periodically changing your encryption keys, you limit the window of exposure if an old key is ever compromised, reducing potential damage. Beyond the core encryption, several best practices can further strengthen your application's overall security. These additional measures create a more resilient and protected system against various potential threats and vulnerabilities. Always validate user inputs rigorously to prevent common vulnerabilities like injection attacks. This crucial practice helps safeguard your application's integrity and data from malicious input, such as SQL injection or cross-site scripting. For web applications, always use HTTPS to protect data in transit, ensuring secure communication. HTTPS encrypts the connection between the client and server, preventing eavesdropping and tampering with data during transmission. Regularly update your IDEs, libraries, and frameworks to patch security vulnerabilities. These updates often include critical security patches that address newly discovered flaws, keeping your software protected against the latest threats. When using data protection APIs, employ purpose strings to isolate cryptographic consumers, adding another layer of security. Purpose strings ensure that data encrypted for one specific use cannot be decrypted for another, enhancing data segregation. Let's now consider a complete, runnable example that demonstrates both encrypting data to a file and decrypting it back. This comprehensive example will tie together all the concepts we've discussed into a practical implementation. This example will include robust error handling and proper disposal of cryptographic objects to prevent resource leaks. Proper error handling ensures application stability, while disposal prevents memory and resource issues. When encrypting, you'll need to consider how to handle different data types, such as strings and integers. Each data type may require specific preparation or conversion before it can be securely processed by the encryption algorithm. Each data type may require specific serialization or conversion into a byte array before encryption. This standardization ensures consistent and correct cryptographic processing, regardless of the original data format. It's also important to understand the trade-offs between security and performance when choosing encryption algorithms and key sizes. Stronger encryption often demands more computational resources, impacting application speed. Stronger encryption often comes with a higher computational cost, impacting application performance. This increased processing overhead means you must balance the desired level of security with the acceptable performance impact for your game. In conclusion, data security is paramount, and encryption plays a vital role in protecting sensitive information. It is a foundational tool for safeguarding game-safe files and maintaining the integrity of player data. By following these steps and best practices, you can implement robust basic encryption for your C# game-safe files. This will significantly enhance their security, protecting them from tampering and unauthorized access. We encourage you to explore more advanced cryptographic techniques and libraries as you become more comfortable with these basics. The field of cryptography is vast and constantly evolving, offering many opportunities for further learning.